Hello everyone, and thank you for having me here. I want to talk about geodesic cuts, and in order to tell you what they are, and maybe also to justify the name, let me start with something that you already know probably, namely geodesic cycles in finite graphs. So what is the geodesic cycle? Well, it's just a finite cycle where for every two vertices on your cycle, the shortest distance between these two vertices in the whole graph is already attained on the cycle, meaning that one of the two arcs connecting them on the cycle is already a shortest path between them in the whole graph. Okay, let's be a bit more general and give now each edge a length. Positive real number, and now we could also calculate distances with respect to this length function and get a notion of geodesicity depending on this function as well, just as before. Okay, but why are these cycles interesting? Well, they generate a certain vector space, and Nathan mentioned it already today. They generate the cycle space of your finite graph. Well, what is this cycle space? Let me recall it again. It's a vector space over the field with two elements, and the elements of this vector space are just edge disjoint unions of cycles. And how does the addition work? Well, take one of your elements and another one, look at the edge sets, and form the symmetric difference. So cancel out all the edges which lie in both. So this space is obviously generated by finite cycles. Oh, it's everything finite here, sorry, by the cycles. But these geodesic ones are maybe a bit sparser set to generate this stuff. Okay, and we have something similar in infinite graphs. But there, we also generate this vector space. But for this theorem, the generating theorem, we need to allow infinite cycles. Nathan mentioned them already. Today, I can't recall it, unfortunately, due to the lack of time. But let me try to state the theorem. So which space do we generate? The topological cycle space. Pretty much defined as before. Its elements are just edge disjoint unions of finite cycles and now also of infinite cycles. Okay, and what is the theorem? The theorem is from 2009. Georgakopoulos and Sprussel proved that this cycle space is generated by the geodesic cycles, which might now be infinite cycles containing infinitely many edges, in your graph. Which graph? Well, locally finite infinite graphs. But we have to take an additional condition on the edge lengths, namely, well, that the sum of all edge lengths is finite. Well, actually, they don't need this condition. They need something, well, a bit weaker, so they have a stronger theorem. But let's stick with this for now, because the other thing is hard to state. And here, generating also means via thin sums, what Nathan told you earlier. Okay, so how should now cuts and geodesicity fit together? I mean, it's a statement about distances and paths somehow on your cycle, and what should this have to do with cuts? So let's look closer again at geodesicity. So suppose you have a cycle which is not geodesic. Well, then you find 2 points on it. Maybe this is now also an infinite cycle, and you have any 2 points there. And, well, you have some path, maybe also a topological one, which is actually shorter than the 2 arcs on your cycle. Okay, and what you can actually show, also for infinite graphs, is that whenever you have such a shortcut, you find a much nicer shortcut, which is a bit more clean. It's a C path, which intersects only in its endpoints with the cycle. Okay, but now this thing tells us much more. Namely, it decomposes the cycle into 2 sets, blue and green, and together with red, each of these sets forms a new cycle. But since red is a shortcut, it's shorter than the segments, each of these 2 new cycles, well, it's a cycle of shorter length. Summing these things together gives you the old cycle back, because the red thing cancels out. Okay, well, this actually is already a proof of the theorem for finite graphs, right? So how does it work? Well, suppose you have a finite graph, and you have a cycle which is maybe not generated by geodesic cycles. Pick a shortest one. This one can't be geodesic. Well, you get such a shortcut, you get such a decomposition. Each of these cycles, blue and red, and the green thing and red, can be written as a sum of geodesic cycles. Well, all your summons are geodesic, the whole thing is generated. Okay. Yeah, but actually this decomposition is not just a consequence of being not geodesic, it's actually equivalent. So maybe again, a cycle is L-geodesic if and only if you can't write it as a sum of precisely 2 shorter cycles. And now this looks much more algebraic and maybe also applicable for matroids. So let's make it just a definition for cuts. So now for any graph which is maybe finite or countably infinite with a summable length function, say that the bond, a minimal non-empty cut, so something which corresponds to cycles, is called L-geodetic if and only if it can't be written as a sum of 2 smaller cuts, bonds. Okay, let me maybe give you a picture because we try to always draw them like this and just to be on the same page. Yeah, so if we have a cut, a bond, which is not geodesic, how does it actually look like? Then one of the 2 sides, the B side, can be decomposed into 2 parts, up and down, and they now canonically somehow define your new cuts, the top right corner against the rest and the lower corner against the rest. So the upper corner contains some edges of the original cut, AB, and something on the B side completely, the red edges. But summing this cut together with the one defined by the lower corner gives you precisely all edges of your original cut, and the red stuff cancels out. And, well, because of our definition, this gives you this definition. We get the same statement in finite graphs to generate the cut space. So the L-geodesic bonds in a finite graph generate the cut space of your graph. Well, and the proof is as before for cycles due to this definition. Yes, okay, but now let me come to the main theorem. And this is, well, this theorem holds also for infinite graphs, but they're also generating another space, namely the infinite cut space. So its elements are now well, finite and also know maybe infinite cuts. And as soon as we have a countable graph with a summable length function as before, this space is generated via thin sums by the L-geodesic bonds. This is a very current result together with Pascal Gollin, and it's not even written up yet. But let me now close with a question or where we are really after it, also together with other people in Hamburg, namely, oh, I have time, okay. Is there maybe a matroidal statement or version of the main theorem, or the one for cycles, which unifies these two generating theorems for cycles, infinite cycles, and infinite cuts? For which matroids? For certain binary matroids. But since Nathan and Katrine already mentioned them, I would replace certain now with cofinitary. Yeah, this is all I wanted to say. Thank you very much.
All right, are there any questions for Karl? Johannes?
You somehow talk about these geodesic cuts, but it's not clear that they exist, right?
Yeah, that's true. But it's maybe also not true whether they exist for cycles, right? So these geodesic cycles might also not exist, right?
Right, but they can believe that they can, like, those cycles are compact for bonds.
Yeah, it really looks a bit weird, but what you actually can do is you can define something which works like a shortcut, right? This shortening path, also for cuts, right? It's this edge set which lies in the intersection of these 2 cycles which give you this thing, and now you can you can also work your way up somehow in deletion minors, approximating your whole graph. And actually what you get is, well, if you have a bond in the whole graph, which is not geodesic, you already notice this on some finite minor, right? And then in this way, you really can build these things or understand it in this way. So they exist. But it's a good point.